You're getting ready to take the TEAS. You're worried about chemistry, have no idea where to begin. Start here, okay? You're doing something really, really brave and courageous by getting ready to take the TEAS. But when it comes to science and chemistry, I bet you feel a lot like this guy in the picture, okay? If I can read your mind a little bit, I bet you have no idea where to begin. I bet that you have no idea what to study or how to prioritize your time, and it's starting to drive you crazy. I bet that when you look on Facebook and when you check out different products, every Facebook post and every review product gives you totally different advice, and you have no idea what to do. And then sometimes when you do take a look at books or videos, they really don't make sense. You know, it feels like you're not really learning. You struggle to understand them. You spend hours reading these books and it's just a bunch of jargon and complicated language and it doesn't really make sense. And then even when you do work through videos and books, as soon as you put them away, you can't remember or retain any of the information that you learned. Does this sound like you? Does this sound like the experience that you've had so far studying for the TEAS? Well, if this sounds familiar, you are not alone, okay? Most people feel this way. There is nothing wrong with you. And if you feel like this, if you've been frustrated trying to study for the TEAS, I made these videos for you. I really think they're going to help. I really think they're going to help you learn the chemistry that you need for the TEAS. This is the first video in my TEAS Chemistry Essentials series. It's a series of 8 lessons. You can see the lessons right here. And they cover the most fundamental, important chemistry topics that you'll see on pretty much every single TEAS exam. Now this series here, as you can see, is totally free, totally free. You can find it at teasinOneday.com. And when you go to that website, I also have study guides and worksheets and flashcards. They're all free and they'll help you learn this stuff. Once you're done with the TEAS Chemistry Essentials series, then you can move on to my full course, which is called TEAS Chemistry in One Day. And this full course covers all of the rest of the chemistry that you should know for the TEAS. Okay, since we're just starting out, let me explain what you can expect in all of these TEAS chemistry videos. I try to do 4 things in all the videos. First, I try to guide you. I want to show you exactly what you need to know and what you don't need to know. I know that a lot of you don't have a lot of spare time, and so I want to explain what your top priorities should be. The next thing I'm going to do is I'm going to teach. I'm going to really teach. I'm going to try to make all of these concepts crystal clear. I'm going to go patiently and step by step. And I'm not going to use any jargon that doesn't make sense. I'm going to try to explain everything in a simple way. You know, there are a lot of videos out there that just have a person saying complicated definitions one after another into a camera. You know, look, I'm sorry, but that doesn't help you learn. So if you've been watching videos like that and you've been struggling to learn the concepts, you've been feeling that it doesn't make sense, the problem isn't you, okay? The problem is videos like that that do not teach and don't help you learn. I'm going to try to do something different here. I'm actually going to teach. I think you'll be able to feel yourself learning. I think you're going to be able to feel these concepts start to make sense. With each video, we are going to practice. We're going to practice problems that are as close to the TEAS as possible, right? You're not learning chemistry for just some random class. You're learning chemistry because you need to take the TEAS and you need to do well on it. And that's what we're going to be constantly practicing for. Every single video, every topic we learn, we'll practice it with TEAS style problems. And lastly, I'm going to reinforce the information that we've learned. None of this matters if you can't remember the information on test day. So I have study guides, worksheets, and flashcards so you can retain and remember the information that you've learned so you can ace the questions when they show up on the test. Okay, so that's what I'm going to try to do in all of the videos. And now I want to get started. This is the first video in the TEAS Chemistry Essentials series. And remember, the worksheets and the study guides, these study resources are really going to help you learn. So go and download them at teasinOneday.com. You get all of these videos. They are totally free at that website. Okay, so the topic of this video is states of matter. You can see here all the stuff that we're going to learn in this video, and I can almost guarantee that these topics will show up on your TEAS exam. By the end of this video, I think all this stuff is going to make sense, and I hope it's going to be crystal clear. So, to begin with, if we're talking about states of matter, well, what is matter? Well, matter is a technical or a scientific or a fancy term for stuff. The stuff in the world around us. All the stuff in this picture here is examples of matter. These things are all stuff. They're all matter. Now, we can take most matter or stuff and sort it into one of three categories. Matter can be a solid, it can be a liquid, or it can be a gas. These different categories, solid and liquid and gas, we call them the states of matter. You'll sometimes hear them referred to as the phases of matter, but we're pretty much going to use states in this video because that's what the TEAS uses. Now, it's probably pretty fair to say that you're familiar with these states from everyday life. Okay, you don't need a video to tell you that bronze is a solid and water is a liquid and air is a gas, right? So that's not what we're going to be doing here. In this video, we're going to be looking at each of these states of matter in more technical detail, in more scientific detail that you might not have learned before. And this technical scientific detail is what's going to show up on the TEAS. The TEAS is going to ask questions about these details that we'll be focusing on in this video. So here's the first of these. The first detail that we need to know is how particles work, okay? If you could zoom into anything, any piece of matter, zillions and zillions of times, you'd see that it's made of tiny little particles. We can think of them like tiny little balls, tiny little spheres, okay? We have some table salt right here, and we have a glass of water, and then we have this zoomed in view. And this shows what these things would look like if we could zoom in zillions and zillions of times and see what they're really made of. And we can see that the table salt is made of particles. Those are the particles. And we can see that the same way water is made of particles, and those are the particles that make up water. So all matter, all stuff is made of particles. Now, these particles, they're not just sitting there. They're not sitting still, okay? The particles are constantly moving around. A fancy way to say that the TEAS really likes to use, because they like to make things more complicated than they need to be, is the TEAS likes to say that particles have kinetic energy. Kinetic energy is the energy of motion. If something is moving, it has kinetic energy. Now, depending on the situation, particles can move in two different ways. The first way they might move is vibrational motion. When particles have vibrational motion, they're just jiggling in place, vibrating. They don't really move. They just kind of squirm and quiver, like antsy kids sitting at their desk in a classroom or something like that. They're not getting up and going anywhere. They're just jiggling, vibrating in place. Okay, so that's vibrational motion. Particles might also have translational motion. You can see the diagram here. In translational motion, particles actually move from place to place. So instead of those little kids, antsy and vibrating at their desks, those kids actually start walking around. They start moving around the classroom, right? That's an example of translational motion. Now, all particles move with vibrational motion and translational motion. But in different states of matter, These types of motion can vary. So maybe particles have lots and lots of vibrational motion, but very little translational motion. Maybe in other states of matter, it's more moderate. And so we're going to be looking at the amount of vibrational and translational motion that the particles have in these different states of matter. That's going to be one thing that's really important. Before we get to the particles, though, we are going to start with a big picture view. We're going to look at these states of matter and take a look at some of the characteristics that we can understand, that we can see with our own eyes, that we can see kind of from our day-to-day experience. So let's start out with solids. I've got a solid right here, and it's a cube of metal. Now, one of the first things that we can say about a solid is that it has a definite shape. Well, what does that mean? A definite shape means that the shape is certain and it can't easily change. Okay? This piece of iron is a cube, and unless we bang it or crush it really, really hard, that shape isn't going to change. We can move the cube from place to place. We can put it in a new location, and the cube is going to be a cube. The shape is certain. Now, something else that is certain in a solid is the volume. Volume is a fancy word that means the amount of space that something takes up. So, for example, this cube has the dimensions of 1 centimeter by 1 centimeter by 1 centimeter. So it has a volume of 1 cubic centimeter. We can move this cube from place to place, put it anywhere we want, and the amount of space it takes up, 1 cubic centimeter, that is not going to change. It has a definite volume, definite shape, definite volume for a solid. And these characteristics apply to all solids. Any solid you see will have a definite shape and a definite volume. Okay, now let's zoom in and look at the particles that make up a solid. Here we have a zoomed in view of the particles. And there are two essential things to notice. First, the particles are close together and they're packed very neatly in an organized way. You can see how they're kind of in rows and columns. The particles are very neatly packed. And because the particles in a solid are so closely packed together, you can't compress or squeeze a solid. You can try, but you can't jam the particles in a smaller area. So you can't take a solid and squeeze it and make it smaller. So for that reason, we say that solids are incompressible. We can't compress them. Now, what about the movement of the particles in a solid? Remember, the particles are always moving and they can move in different ways. Well, the particles of a solid have high vibrational motion. They're always quivering in place, just like that. But they have very little translational motion, low translational motion. They aren't moving from one place to another. They're stuck in place. They're just vibrating right where they are. So these are the important characteristics of a solid. The big picture view here, and then the smaller microscopic picture here about the particles. It's important to know all of this for solids. Now, let's move on to liquids. Here we've got a liquid. Maybe it's some water or something that we have in this flask. Now, a liquid has an indefinite shape. That means that the shape isn't certain, that it can change. Well, what does this mean? Well, a liquid flows freely, so it takes the shape of its container. Here, in this flask, the water has this sort of triangle shape, and that comes from the container, the flask that it's in. But if we poured this liquid into another container, like the glass or the bottle or the beaker, the liquid would take on different shapes of those containers. So that's what we mean by indefinite shape. The shape changes based on the container that the liquid is in. However, a liquid has a definite volume. The amount of space that it takes up doesn't change. So, if we pour the water from the flask to the glass here, it would always take up 750 milliliters of space or volume, even though the shape is changing. So liquids have an indefinite shape, but a definite volume. Now, let's take a closer look at the particles in a liquid. If we could zoom down and see the particles in this liquid, this is what they look like. Now, what are the important things to see here? First, we'd see that they're pretty close together. They're not packed neatly, though, the way the particles are neatly packed together in a solid. So they're close together, but they're not packed neatly. Now, the particles of a liquid move more freely than the particles of a solid. They wiggle and they sort of swim around each other. Okay, they're in motion. That's what allows liquids to flow. Now, when we look at the types of motion for the particles, they have moderate vibrational motion, so they're jiggling a little bit, but they also have moderate translational motion, which means that they're moving around. They're not fixed in place, but as we said, they're kind of swimming around past each other. Now, even though the particles in a liquid are looser and they're not as neatly organized in a solid, as you can see here, there's not much space between them. They're still pretty close together, and that means that we can't really squish them any closer. So liquids are also hard to compress into a smaller space, and we say that liquids are incompressible. Okay, all of these characteristics that we talk about are true for every liquid that you'll run into. Indefinite shape, definite volume, and all of this information about the particles and their movement. Now, let's move on to our last phase of matter, our last state of matter, which is gases. Here we have a gas. A gas has an indefinite shape and an indefinite volume. Here's what that means. The shape of a gas will change to fit any container that it's in, just like a liquid, okay? Put the gas in a container with a different shape, and the gas's shape will change. But the volume of a gas also changes. Check this out, okay? Right now, this yellow gas has the same shape as the flask. But if we remove the top, the gas would expand to take up a larger volume, okay? Gases can expand or contract to fill whatever container they're in. Now, let's zoom in and look at the particles. Here's our zoomed in view of the particles. What are the things that you notice? First, the particles are spread really far apart. They're really far apart from each other. And if we could watch them in motion, we'd see that they were flying around. Zoom, 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 moving around really, really fast. Now, they fly around super fast, but they don't wiggle very much. They're mostly spending their time shooting from place to place. So gas particles have low vibrational motion, but very high translational motion. Now, this explains why gases can expand. You give them a bigger container, and since they're always flying around, they just fly out and they fly until they take up the whole container. They just fly further and further apart. Unlike solids and liquids, gases can be easily compressed. They are compressible, and you can probably see why. There is so much empty space between these particles, you can just squeeze them closer together. A great example of this is a scuba diver's tank, okay? A little tank like the one that a scuba diver carries on their back has enough oxygen to breathe for between 30 to 45 minutes. It's just all compressed. All the particles are squeezed into a very small space. So gases, unlike the other two states of matter, are compressible. Okay, and here's a heads up on a word that the TEAS will try and trick you with. Vapor, right here, is another word for gas. Technically, it's gas at a low temperature, but don't let that confuse you, okay? If the TEAS says vapor, you should think gas. Vapor, gas. All right, so all these things we talked about are the important characteristics for all gases. Before we move on, let's briefly talk about one other state of matter. That's plasma here, which is sometimes called the fourth state of matter. Now, plasma is sort of like a special gas created by lots of heat or lots of electricity. It's important in astronomy. Plasma is in things like the northern lights and stars and nebulas. Honestly, we don't have a lot of exposure to plasma in our daily life. It's also in lightning. It's in neon signs. It's in these glass globes, the hippies really love. But look, don't worry about plasma. That's the important take-home message here. The TEAS pretty much only uses plasma to trick you and to distract you from the other important states of matter: solids, liquids, and gases. The right answer on the TEAS is pretty much never going to be plasma. But there is one thing you should know, particularly for the TEAS in healthcare. The plasma that we're talking about in stars and hippie globes is very different from blood plasma. Okay, don't get confused about that. Blood plasma, you can see it here in a sample of blood, is actually a liquid, okay, and it has nothing to do with the plasma that makes up stars. Okay, so don't get confused by that. The blood plasma is definitely not the fourth state of matter. Okay, now that we've talked about all this, let's review what we've learned, and then we'll do a whole bunch of practice TEAS questions. So, the three main states of matter are solid, liquid, and gas. A solid has a definite shape and a definite volume. Its particles are closely packed together in a very organized way, as you can see here. The particles have high vibrational motion and very low translational motion, and a solid is incompressible. A liquid has an indefinite shape. It takes the shape of its container. But a liquid has a definite volume. Its particles, you can see them here, are not packed as neatly as the particles in a solid, but they're still pretty close together. The particles in liquid have moderate vibrational motion and moderate translational motion. Liquids can flow into different containers, but they are incompressible. You can't squeeze them closer together. And finally, gases have an indefinite shape and an indefinite volume. They take the shape and the volume of their container. The particles in a gas, as you can see here, are very far apart and they move around very quickly. They have low vibrational motion, but very high translational motion, moving around like that. Because there's so much empty space between the particles in a gas, gases are compressible. You can squeeze them into smaller volumes. Now that we've talked about all this, let's try a couple of TEAS questions. Which of the following samples of water maintains a constant volume but takes the shape of its container? First off, let's look at the state of matter for each choice. Okay, ice is a solid, room temperature water is a liquid, and water vapor and steam are both gases. Now, you might have been a little bit thrown off by the term vapor. Remember, vapor usually means gas at a low temperature, but don't worry, just remember that vapor is still gas. The state of matter that maintains a definite volume but an indefinite shape is a liquid. A liquid takes the shape of its container, but it always takes up the same amount of space or volume. So choice B is the correct answer. It's the only one that's a liquid with a definite shape and with a definite volume and an indefinite shape. Here's another typical TEAS question. Which of the following terms describes a compressible sample of molecules having high translational motion? And then we have these 4 choices. Let's think it through. What state of matter is compressible? What state of matter can be compressed? Only gases, right? Solids and liquids are incompressible. And which state of matter has high translational motion? That means that the particles are free to zoom around. Well, that's gases too. So the answer is going to be choice C, gas. Remember what we said about plasma? Plasma is almost never an answer, and the TEAS really likes to use it to distract you. Okay, another question. Which of the following is true of gases? Well, as TEAS questions go, this is pretty straightforward. We just have to remember the characteristics of a gas, okay? A gas takes the shape and volume of the container that it's in, which means that they do not have a definite shape and do not have a definite volume. This is the only choice that could be correct. Okay, last one. In which of the following states of matter do particles have the highest vibrational kinetic energy? Okay, remember that there are 2 ways that particles can move. Vibrational motion, which is back and forth, and translational motion, which is place to place. As you go from solid to liquid to gas, vibrational motion goes down and translational motion goes up. So vibrational motion is highest in solids. Remember, the particles in that solid are jiggling around just like that. And the answer is D, solid. So that's our states of matter. Know these characteristics about solids, liquids, and gases and the particles that make them up, and you'll be in good shape for the TEAS. So that was the end of our first video in TEAS Chemistry Essentials. I hope it made sense. I hope it was crystal clear. Now, make sure to review and practice the stuff you learned in this video by looking through the worksheets and study guides you can find for this lesson at teasinOneday.com. And then you're ready to move on to the second video in the series right here, state changes, video number 2. You can find all of these TEAS Chemistry Essentials videos at teasinOneday.com. I'll see you in the next video.